Hi, welcome to section 5.2. This is the last section in winter term. So we're going to talk about compound interest. This is something that's done in two main ways, and one of them is by compounding periodically, meaning they take your interest rate, they cut it up, and then they apply that interest rate multiple times throughout your year. And then compounding continually, that's where it's compounded just nonstop. It doesn't stop compounding your interest. So in both of these equations that are here, the letter P stands for the principal amount. The letter M stands for the number of times a year. The letter R is your interest rate. T is the years that you're going to save or the years that you're going to pay it off. And A is the balance in the account. So how much you have at that time. One thing that can really confuse people is how to go from percentages to rate. So you're just going to move the decimal 2 places to the left. Oops, I forgot a whole word. Move the decimal 2 places left. So, 1, 2, that'd be 0.08. 1, 2, 0.045. Part C would be, 0.0135. D would be 0.18. And E would be 0.0036. So let's try a problem. If $5,000 is deposited in an account earning 3% interest for 5 years, that would mean P is 5,000. Interest rate is 0.03 based on what we just learned, and T is 5 years. So to do this problem, though, one thing I wanted to bring up is that people sometimes have trouble with words in this kind of problem. So just so that we're all on the same page, bi-monthly means twice per month, and that means that M is 24, because 2 times 12. Annually means once, and M equals 1. Semi-annually means twice, and that means M equals 2. And quarterly is M equals 4. So for the rest of this problem, and actually it's a whole new problem, I'm supposed to calculate the value of the account above when it is compounded yearly, monthly, weekly, and daily. So yearly, that's 1, monthly, that's 12, weekly, that's 52, and daily, that's 365. Although I think this year it's 366 because we had a leap year. But don't worry about that. You can just use 365. So to set up each one of these, it would be, 5,000. 1 plus the rate, which was 0.03, over the number of times, which is 1 in this case, and then 1 times the number of years, which was 5. Okay, and if I do that, I get $5,796.37. It's pretty cool. It's a little bit of money there. For part B, it's very similar. 1 plus 0.03 over 12, and then 12 times 5. Okay, calculator time. Okay, if we do that, we get $5,808.08. Part C, 5,000. 1 plus 0.03 over 52, and then 52 times 5. Okay, putting that into a calculator gets me 5,808.91. So there was a pretty big leap from part A to part B. 90, pretty darn big leap. But to go from part B to part C, that's less than $1 difference. So I'm betting it's an even smaller difference to go to part D. But part D 1 plus 0.03 over 365, and then 365 times 5. So that is 5,809.13. So it went up roughly like, I don't know, 70 cents from part B to part C. But then from part, C to part D, it went up even less than that. It's kind of an interesting thing to keep in mind. So let's see the next problem. Would it make that much of a difference if you invested in an account that was compounded continuously at the same interest rate for 5 years? And I would have to guess no, given how slowly this is increasing. Like we're increasing less and less each time. But we might as well find out. 5,000 e to the r, 0.03 times 5. Okay. 5,809.17. Okay, so yeah, that actually went up roughly 4 cents. A 4-cent difference. So it turns out it doesn't make that much of a difference between these two. Those two, not much of a difference. All right, number 5. $4,000 is invested at 2.75 interest compounded continuously. Okay, so this is my R, and this is my principal amount. What function models the value of this account? P e to the RT, or 4,000 e to the 0.0275 t. What will be the value of the account in 10 years? So 4,000 e to the 0.0275 times 10. Okay, I'll stick that into a calculator. 0.0275 times 10. That is $5,266.12. C. At what rate will the value of the account be changing in 10 years? Okay, so derivative. I want to have, so say y equals 4,000 e to the 0.0275. The derivative would be, so I'll leave the 4,000 alone, and then e to its exponent stays the same. And actually, I forgot the t up here. But then I'm going to multiply by the derivative of the exponent, which would be 0.0275. And then I want to evaluate that when t is equal to 10. So 4,000 e to the 0.0275 times 10, and then all of that multiplied by 0.0275. .0275 times 10, and then all of that is going to get multiplied by 0.0275. Okay, so I get approximately 144.82. So the units here is going to be y over t, And as you recall, this is telling me the amount in the account. So it's a change in dollars per year. So roughly, the money in the account is increasing by about $150 a year. So that's nice. That's comforting. So part D says, how many years will it take for the value of the account to double? So it started with 4,000, so 8,000 is double. And then I would divide by 4,000, but I already know that's 2. I keep forgetting to put a t, sorry about that. Then I take the natural log of both sides. Natural log of e. It's going to cancel and leave me just with the exponent. So t is going to equal the natural log of 2 divided by 0.0275, which I will approximate. So that is approximately 25.21 years. And I think this makes sense to me because when we checked in 10 years, it had gone from 4,000 to 5,000. So that it makes sense that it's a little bit, farther along, roughly 25.21 years. I'm going to pause there for questions.